Welcome, everyone. My name is Ryan Harter. I am the Android developer at a small company called Pixite. We do creative graphics apps. We used to do a lot of photo editing stuff. Our big app now is an adult coloring book called Pigment. Most of our stuff is in OpenGL, but we also do a fair bit of these graphics types of things using the Canvas APIs built into Android. So today I want to talk a little bit about how you can use the Canvas APIs to draw on the screen or on bitmaps in 2D and really get some good wins there. So to start out, just if you're not familiar with the Canvas, you can think of it like the name implies as just a surface on which you can draw, all right? Canvas has a bunch of methods that allow you to draw shapes and different things, which we'll get into. But it's really just a surface on which you can draw on Android. And so the way that it's used in Android is for drawing views, is sort of the primary use case on Android. So the way that Android draws views is you have, at a very high level, you have your view. That might be your text view, image view, anything like that. And those, in their onDraw method, are actually going to draw to a canvas. And that canvas is what we're going to be looking at today. But from there, it goes into a couple of different places. There's keynote crashing, which is fun. My apologies. Where were we? All right. All right, so we have Skia. All right, and to be honest, I'm not even sure if Skia is really used a whole lot anymore for view drawing. Skia is the software renderer, so before Android devices sort of all had GPUs and hardware accelerations, you would use Skia to draw, and that was software rendering, it's a really great API. I'm not really sure actually if it's even still used much for view rendering now that we have the OpenGL renderer. So with the introduction of OpenGL 2.0, or rather OpenGL ES 2.0, we got the GLSL shading language and shaders, which made OpenGL really performant, and so that's kind of how we render things now. Those two, you don't really ever need to touch, all right? I've never actually heard of anybody outside of the Android framework team working with Skia directly. And the OpenGL renderer is sort of a backend for the canvas. So you work with the canvas and it translates your commands to these two renderers. So we want to draw to a canvas, right? So how do we get a canvas? Well, I mentioned in that diagram that you can get, a real common way to get it is in a view, right? The onDraw method doesn't create its own canvas, it's given a canvas. And that canvas is used to draw to the screen. Any drawing you do there will be drawn within the bounds of that view. Another way to get it is a drawable. You make a custom drawable, and it has a draw method, very similar to the onDraw method in View, where it's given a canvas, and then you can draw to that canvas, you're sort of confined to the bounds of that drawable with the canvas. And the last way that you can actually create your own canvas is with the bitmap. So a lot of times the canvas is used to draw to the screen. In some cases, you might want to actually render some custom drawing into a bitmap. This could be for, maybe you want to cache a profile image, and so you want to crop it and put a mustache on it. You can do that. Put it to a bitmap, write it to disk as a JPEG or a PNG, and now you've got this cached image that you've drawn, and you don't have to worry about redrawing it every single time. As far as everyday functionality goes, that the bitmap version is the only real case where you create your own canvas. In other cases, the canvas is given to you. So now that we know how to get a canvas, the question is, what can we do with it? All right, I mentioned before that a canvas is just a surface on which you can draw, and the Canvas APIs come with just a whole slew of simple methods that allow you to draw primitives. So you can draw rectangles, or squares in this case. You can draw circles. You can draw arbitrary paths. And one thing you'll notice from this slide is that as you're drawing to the canvas, everything is sequential and sort of builds on top of it. So this path actually draws over the top of the other items. And that's kind of how it works. It's very procedural. You draw to the canvas, and those pixels are drawn and show up on top of the other things you're drawing. You can also draw, or you can transform the canvas. So in this case, we shrunk the canvas down a bit. And that gets really useful. We'll get into that a bit later. You can then draw some more arbitrary shapes to it, right? And here we have a donut. And then you'll notice we shrunk down the canvas before, and then we drew our donut. And then once we restore its size, now we have a giant donut, which is even better. There's a whole lot more that you can do. But for now, we're just going to dive into the basics of canvas drawing and show how to do that. And I can't think of a better way to demonstrate that than using the donut. So before we get started actually drawing ourselves a donut, I want to talk a bit about why we want to draw this with the canvas. This is a fairly simple image, as you might expect. So why would we want to draw this manually instead of just including a PNG in our resources and loading it that way? And there's a few different reasons for that. Perhaps you're not a fan of chocolate and you would rather have like a mint frosting or icing on your donut, right? So we can, we can change individual pieces of this donut. Maybe you want like a red velvet base to your donut. That's a great choice. Love those. Maybe you don't like as many sprinkles and you just want a few sprinkles and you sort of want to concentrate them in different areas. There's, nothing wrong with that. It's not my preference, but we can do all these types of very fine-grained control of our donut by drawing it manually, as opposed to including all of these images. Maybe you just want a nice slim APK, and for some simple image like this, we'll demonstrate here how we can actually draw this donut, and it doesn't take that much code to draw ourselves a donut, and it's certainly a lot less than a bunch of different resolutions of a PNG of a donut. So it can provide a way to sort of slim down your APK. Lastly, maybe you want to animate or move all of these individual components separately. For instance, and boy, I wish I had thought of this before, but you might want to make the donut wave. Yeah, you can do that with Canvas APIs. For whatever reason you choose to use the Canvas APIs, we're going to take a look at how to draw this donut today. So to start out, as I mentioned before, drawing with the canvas is a layered approach, so we need to start with the base. All right? And as we break apart this image, you'll notice it's just simple shapes. All right? It's a circle and another circle. That's how we make our donut. So let's take a look at drawing this with the canvas. And for now, we're just going to ignore that inner circle. So as I mentioned before, the Canvas APIs have some really simple draw methods to let you draw simple shapes and that sort of thing. And they're pretty straightforward. They all kind of start with draw as the word. In this case, we have a draw circle method. And what we need to do, we need to give it the X and Y coordinates of the center of our donut. And then we need to give it the radius, which in this example, just so you know where all of this is coming from, this is a donut drawable. So the drawable has bounds. So the radius of our donut is just going to be half of the bounds. So that way our donut will fill the drawable. So that's what we give it as far as to tell the canvas where and how to draw this circle. And we also give it the paint. So what is that? In the earlier part, we were telling the canvas what to draw, okay? Draw a circle with this radius at this location. Well, the paint is what tells the canvas how to draw. So paint is just a simple Java object, right? And it stores a bunch of state that tells the canvas how to draw. So on this paint, we're going to make just a base paint, and we're going to apply this plain cake donut color to it, all right? So By default, paint fills, but you can also set it to stroke. You can set it to stroke and fill. And you can set all sorts of different things on the paint, like stroke width and text and font information and all that sort of stuff. But for this, we just need a simple fill paint, and we are going to set the color. And this is something you'll notice, as opposed to instantiating a paint in our draw method, we don't want to be instantiating new objects and draw methods and that sort of things, because it can be resource intensive. So this is a property on our drawable, since it really doesn't change a whole lot. And that's all it takes. That's the base of our donut. But this isn't really a donut, this is a biscuit, right? Because we need the hole. That's what makes it a donut. So now that we've drawn the base, it would be pretty simple to think, okay, we've got the donut base there. I know how to draw a circle, so I'm just going to draw a white circle. But that really poses some problems because we don't know what this donut is going to be on, right? Presumably a plate of some sort, but we don't know what color, so we need to be able to see through that. So we need it to be an actual hole. Now the canvas has methods for doing this, and this process is called clipping. So here we have a clip path method, and what this is going to do in this particular case, because we're giving it the region operation of difference, it's going to basically say, when we give it that circle path in the center, it's going to say only draw pixels that do not intersect with this shape. So what happened here is that the canvas just ignored any pixels that intersected with that whole path, and so we're only drawing the outside, which means we can see through it. The other option is to draw the intersection if you want a donut hole, but nobody wants that. So we're going to use the difference. And then we'll give it a path. And so this is a little different. Before we just drew a circle, right? Now we have a path. And a path is another Java object, and basically a path is a way to just record drawing operations. Just like you can draw to the canvas, a path is a way to sort of to cache all of those drawing operations into an object. One thing to note is that the donut hole doesn't change on every draw. It only changes when the bounds change. So we only need to update the whole path when the bounds change. So there we will reset the path in case the size changes or we animate or anything like that. We need to make sure we're not just adding circles on top of it. So we reset it, and then we add a circle. And this looks very similar to the drawing of the base. You can see we give it the center X and Y coordinates, and we give it the radius. And then we have this direction, right? This, in this case, it's clockwise. The alternative is counterclockwise. For this type of example, it doesn't really matter. That kind of thing matters a bit more when you're doing different types of more advanced stuff, but for now, we can just ignore it. And there we have our donut hole, all right? So one of the things to keep in mind about this clip path is that since we clipped the canvas, every draw operation after that clipping is now going to be clipped, right? So let's say we want to class this donut up a little by adding a mustache, all right? Right now, if we do that, since we clipped, we're actually going to clip off the top of the mustache. So, it doesn't look terrible, but it's not ideal. So what we need is a way to restore the canvas to its previous state before we clipped it. Now, Canvas has a built-in mechanism for this, which is simply called save and restore. And what happens is any operation that's going to modify the canvas, so clipping, any sort of transformations like translate, scale, rotate, that type of thing, anything that adjusts the matrix of the canvas, anytime you do that, before you do it, you want to save, and that's just going to save the current state of the canvas when you started the change. And then afterwards, you just restore. And that's sort of a super easy method to just go back to the previous state of the canvas. So right now, we're going to wrap our clipping and all of the drawing that we want to be clipped inside a save and restore. And that way, when we draw the mustache, after we restore, the mustache is not clipped. But, who eats donuts with mustaches? So we don't really need that. All right, so moving on. So right now we've clipped the hole, we've drawn the base. What we're looking at right now is a bagel, right? We could stop here, but I promised you a donut, so we're gonna have a donut. In order to do that, we need to add some icing. Now, when you get icing on a donut, it's not usually very uniform. It's sort of random as, whoever spread it on. And so you can see we've got these random curves around here. And that could be a really complex thing to have to calculate all by yourself, to figure out curves and that sort of thing. But Canvas has some built-in functionality for this, which is really helpful. If you notice, the icing is pretty close to a circle, right? There's some random fluctuations in there, but it's basically a circle. So what we can use is a functionality of the paint called path effect. And what path effect allows you to do is take any path, like a circle, rectangle, arbitrary paths or lines, and modify their geometry before they're actually drawn to the screen. So what we're going to use is a couple of these. We're going to use a discrete path effect, and I'll explain how that works with this handy-dandy blue circle, right? So it's really easy to see. Basically what the discrete path effect is going to do is it's going to break up a path into line segments, all right? It breaks it up into segments of 60 arbitrary units of measure in length. And then the second argument is a deviation. So each of the vertices of this broken up line segment are going to be moved within that deviation of 25. So this is how we get sort of that randomization. But that sort of looks like a PlayStation 1 donut icing, right? That's not really something we're after. So we need to take a look at another path effect, and it's called the corner path effect. And as you might imagine from the name, all the corner path effect does is round corners, all right? So we give it a radius, and it will go ahead and round the corners of that. And so now we've got this delicious looking icing. On each paint, though, you can only set one path effect. So there's a couple of different path effects that basically just combined other ones. And we're going to use a compose path effect, which is a bit confusing. The way the compose path effect works is it first applies the second argument, and then it applies the first argument to the result of that. And if you read through the documentation, you can kind of understand why they do that, because they envision it as an inner-outer thing. But I don't know. To me, it looks a bit confusing and backwards in practice. But that compose path effect will combine these two, and then we'll just set that to the icing paint, right? To the path effect on the paint. And that way, all we have to do is, like we did before, we just draw a circle. And you'll notice the only difference here with the previous circle I drew for the base was the radius is a bit smaller. I divided by the width by 2.1 instead of 2, because we don't want the icing to go right up to the edge, because we need a place to hold our donut. And then we're using this icing paint instead of the base paint. So a couple of different paints for the different things we're drawing. The last thing we need to do, because nobody wants see-through blue outlined icing, is we need to set the paint color to chocolate. All right, so that's how we draw the icing. So this donut's starting to look pretty good, right? But, it's not quite jazzed up as much as I like a donut to be. I want some sprinkles. All right, so you can see here, sprinkles are pretty straightforward. As we're looking at breaking all of this stuff up, a sprinkle is really just a very small rounded rectangle in a random area, right? Random position. So what I've done for this drawable, this class, and I didn't make a slide for this, I'll just describe it. Each of these sprinkles is represented by its own class, all right? It's a very lightweight class that includes an int to keep track of its color, and float to keep track of where where it exists radially on the donut, so what angle it's at, its individual angle at that point, since they're all pointing in different ways, and then the distance out from the center of the hole, right? Pretty straightforward. It's like 1 int and 3 floats. So, how do we draw these? Well, there's a few steps that we need to do for each of these sprinkles. We need to calculate the position. The sprinkle stores that information, but we need to determine it based on the size of the donut and whatnot. We need to move the canvas, and I'll talk about why we're moving the canvas in a minute. We need to draw the sprinkle, and we need to restore the canvas. As I said before, anytime we modify the canvas, we need to restore it. Just sort of a side note here, if you were to have a custom view, for instance, and you did not take care of saving and restoring state, the reason that you need to do that is, say you clip the canvas, say I clip the hole out of this canvas. When it's drawn to the view, it is given the canvas. I don't own that canvas, right? And I don't know, maybe there's some other view that's going to show up on top of this view, for instance. Now, if I clipped that canvas and I don't restore its state, when the container view tries to draw another view on top of it, now it still has that clip or that transformation or whatever it might be, right? Since we don't own this canvas, we need to make sure that when we're done with it, it's in the same state as when we started. So that's why we're restoring the canvas after all of this. So let's look at these step by step. The first one is really not super important. It's just a little bit of math to figure out, to modify the distance. I'm storing the distance as a float from 0 to 1, and that sort of tells you how far from the inside of the ring to the outside of the ring you are. And this is just a little bit of math that's very specific to donuts to figure that out. Once we have that distance, now we can go about moving the canvas. Now, the first thing we have to do is save the state, right? Anytime we modify the canvas, we need to save its state. Now, one of the things that that you'll notice is that we already clipped the canvas earlier, right? And we wrapped that in a save. And now, in each of these sprinkles, we're also saving the state. So basically, this is like a big undo stack, right? So every time you save the state, you can save deeper and deeper and deeper, and then you just restore your way back out. And save and restore has a mechanism by which you can, if you're being irresponsible and you're not really confident that you're saving and restoring as you're supposed to, when you start drawing, you can actually get an int value which says the current state that you're saving. Because each time you save, it increments a value, how deep you are in that save stack. And so then at the end, you can just say restore to state 3, or whatever int you get. You shouldn't really ever have to get to that point, because you should be responsible. Anytime you call save, you should call restore. But that's where we are. So we've saved our state. The next thing we're going to do is we're going to rotate. And this angle is tells us where we are on the donut, right? This is so as an example, the sprinkle that we're going to draw is down in sort of the bottom left area, right? It's at the end of that red line. So what we're going to do to make this really easy is we're actually just going to rotate our donut so that that angle is straight up and down. Okay, the user never sees this. This is all happening behind the scenes before things are rendered. But we're just going to rotate the canvas to get that in the right position. That way, translation becomes really easy. We calculated our distance from the center before. All we need to do is translate along the y-axis that distance, and that centers the final position of the sprinkle in the center of the screen. You'll see why that's important in a few minutes. Lastly, we're going to rotate again, and both of these times we're rotating around the center of the canvas. So now that we've got the center in the final position, the donut would look really weird if all of the sprinkles were sort of at the same angle. So now we're going to rotate again to determine the actual rotation of the sprinkle itself in its position. So this is actually the final position for this sprinkle in the center. And next up, we simply have to draw our sprinkle. Now, it can seem a bit backwards that when we want to draw a sprinkle at a certain XY coordinate, you might wonder, why are we moving the canvas and doing all of this stuff instead of just drawing the sprinkle there? Well, you'll notice my rounded rect code there is super simple, right? We're drawing at the center, the CX and CY are the center X and center Y coordinates. So we're drawing at the center, and it's just a rounded rect, and every one of the sprinkles is going to be identical. I don't have to do all of this complex math to figure out, you know, if it's going to be this distance, but it's at an angle, how far left and how far up is that? I just get to draw a sprinkle right in the center. Another thing you'll notice is I use a sprinkle paint. I mentioned before that each of the sprinkles is a very, very lightweight object of 1 int and 3 floats. Well, another option would be for each sprinkle to have its own paint, right? Since paint is what describes the color and that functionality, each sprinkle could have its own, but there are a few issues with that. First of all, it makes a sprinkle hard to serialize. If you want to store this donut for later, we need to serialize it in some fashion, right? That could be JSON, it could just be a bundle, but storing it as a paint is going to make it hard to serialize. The other thing is that we can use a single paint and just change the color on it. So things are going to be more efficient since we don't have a whole bunch of paint objects in memory. For this donut, you know, right now it only has 1 sprinkle. It might have 100 sprinkles by the end of this. If we have a donut with 10,000 sprinkles, it gets really expensive to initialize and store all of these different paint objects. So we can just cache a single paint object and reuse it. And then we draw a rounded rect. And this is pretty straightforward. We give it left, top, right, bottom, just like any other rect. We give it some corner radiuses, radii, and then we give it the sprinkle paint. All right, and that's how we draw our sprinkle. And then, of course, the next step is to restore the canvas. Since we modified the canvas before, we're going to restore it, and that just moves it back to where it's supposed to be. And what that allows us to do is very quickly step through all of our sprinkles so we can draw all of the sprinkles onto the donut. All right? And every time we're moving the canvas and then drawing our sprinkle right in the center and then moving the canvas back, the user never sees that. At the end, they just see the finished sprinkles. So that's kind of the high level of how we're drawing our sprinkles. So this is our donut, right? We've drawn a complete donut here. We've clipped the hole, we've drawn the base, we've drawn the icing and the sprinkles. And as I mentioned before, we wrapped all of that in a save and restore state so that the next thing that wants to come draw something to this canvas isn't modified by what we did. And that's great. We all get to go home and eat donuts. But then your product manager, or whoever it might be, comes in and has some different requirements for you. And now they want a smaller donut. They want a mini donut. And so this can be problematic, right? You might think, you know, we did all of that math through there, right? It was really simple to figure out, you know, our radius was just half of the width. That was real easy. The sprinkles are a certain size, drawn right in the center. That's great. So now you might be thinking, well, we have to go through and we have to modify all of that math, right? But that's, of course, not very reusable. What happens when the requirements change and he wants a giant donut or whatever it might be? So instead of changing any of that code that we've drawn, what we can do is simply modify the canvas. So in this case, to get a donut half the size, all we need to do is shrink the canvas by half. Now, one of the things, if you've done other sort of graphicsy matrix stuff with MVP matrices and that sort of thing, is that this seems a little backwards, right? If you were to scale the canvas down and draw something on it at the same size, once you scale that canvas back up, you would expect that object to be larger, right? So it's worth noting that the operations here on the canvas, we're not actually scaling the canvas. What we're doing is the canvas contains a matrix, and we're modifying that matrix. And so what this does is it adds a scale matrix at 0.5 so that every future drawing call will be modified by that matrix. So what we're really doing when we say canvas.scale is we're saying scale all future draw calls by this amount, as opposed to scale the actual canvas by this amount. And of course, since we're modifying the canvas, we need to save and restore. All right? So now we've been able to make a donut half the size without ever actually changing our drawing code. So our drawing code is super reusable and flexible. And now another change comes in, right? Now we want the user to be able to actually modify the size of our donut. Well, that also becomes super easy. Because of that canvas scale call, we simply add a float property that's a scale, and now we've got a donut that can scale to whatever size the user sets. And these calls, they certainly can be done in non-optimal fashions, but this is actually really performant to draw this way. All of the math for scaling and that sort of thing stayed the same. We're just scaling the canvas. And so that's how you can draw a donut. And so if you're interested, there's a sample app called which is on my GitHub page. And you can also find the slides on Speaker Deck. And with that, I will take any questions. Yeah. No questions?
Where'd you get the donut?
I have this much left. I walked down to Safeway after lunch. Any other questions? Yeah. So the question was if there's a performance implications to modifying the canvas as opposed to just drawing the sprinkle, where you want on the canvas. So there's a couple things there. First of all, one of the challenges of drawing the sprinkle where you want on the canvas, as far as I know, it wouldn't really actually be possible with the canvas APIs because we rotated that sprinkle. And so when you draw something like a rounded rect, if you were to draw a path, it would work fine. But when you draw a rounded rect, I'm going to get chocolate all over my computer if I don't remember this. But when you draw a rounded rect, you give it a left, top, right, and bottom. And so rectangles, as far as Android is concerned, are always oriented straight on. And so we have to rotate the canvas a little bit, right? But if you remember, when I mentioned that we're not actually modifying the canvas, we're modifying a matrix that all draw calls are being passed through. So that, as far as I know, and I'm sure there's people here that could correct me on this, makes it effectively free. Because all of the math that we would have to do to figure out where that sprinkle's supposed to be, and if you've ever had to do it, it can get quite complex with sines and tangents to figure out a distance at an angle and translate that to x, y. Instead of having to do any of that in Java and do the actual math for it, all we do is we give it a value, and that gets passed through a matrix to draw on the final canvas. So, and that canvas, I believe, it's like a float array of 16 bits. So for the most part, that's effectively considered free. Yeah, the question is, what happens when you save the canvas but forget to restore it? That's a good question. You screw up everything you try to do later on. So it depends on where you are. Theoretically, what would happen there is that, let's say that clip that we did for the donut hole in the center, we're modifying parts of the canvas that affect future draw calls, right? So let's say we forgot to restore after that, or we scaled in this slide. We're setting the scale on the canvas, on the canvas matrix. If we forgot that last restore call, what we would end up with is anything that comes to try to draw on this canvas later on is going to be scaled like that as well. So some of these things like clip paths, so we clip to the difference, right? To get outside of that hole. Some cases you might want to use that is, for instance, if you're trying to draw a user avatar or something like that, you might want to clip it to a circle or a rounded rect or something, and then you would do the intersection. Well, if you forget to restore, now everything that draws after that, which might be a label or a badge or anything that goes on top of that avatar, is also going to be clipped. So I think in practice, a lot of things like views, when the view passes the canvas to you, to your custom view or a child view, this is pure assumption, so I wouldn't roll with this in production. But what I would assume they would do is keep track of the state. I mentioned that each state has a number. So before they do that, they would get the current state as an int. And then after they draw a child, for safety, they might restore to that number in case it's not there. But basically, it just affects every future draw call. Yeah. So the question is, why did I clip the hole at the beginning as opposed to the end? Because there are some sprinkles in the middle. First of all, if you go to github.com/rharter/r/harter/, you'll notice that there are actually no sprinkles in the center. The sprinkles that showed up in the middle were purely keynote foo, me trying to scale things and move all of these independently. Because the canvas is clipped in the beginning, it's not going to draw any pixels in that circle. If you're not careful, it might cut off a sprinkle in the middle, but such is the danger with donuts. Any other questions? Yeah. Okay, so the question is, how many draw calls do you need to have worse performance than just loading a bitmap? The answer is I have no idea. A lot of it's going to depend on what you're drawing. And so, the suggestion here is not that you should be replacing every icon and every drawable in your app with something you've drawn custom with the canvas. There were some things that we talked about before where if you want to animate individual components of this, you can do that sort of thing. If you want to transform it in certain ways. In the sample app, there's actually an animate button which will actually make all of the sprinkles individually rotate. So that's the kind of thing you can't do with a bitmap, right? And so that might be a reason you want to do this. Another thing is if you want to modify another image, right? So the user avatar, that's a really good example. In cases where I've written apps where we take a headshot of somebody and clip it to a circle and then draw like a silver border around it. And that's super simple with the canvas. But I mean, you wouldn't want to do everything. And one thing to note is that path object, it has very similar semantics in what you can draw to the path to SVG paths. So you can do the type of operations where you're doing curves and lines, to different coordinates and that sort of thing. So a lot of SVG drawable type of operations are actually using the canvas to render an SVG path to a bitmap. Okay, yeah, so the question is what's going to the GPU? Is it textures or paths or that sort of thing? I don't know exactly. My understanding is that there's a lot of work with textures. So one of the things you'll notice in the larger donut, I mentioned the discrete path effect, right, to get the icing. Well, you'll notice down in the bottom it's actually clipped, right, and up at the top too. And, I would blame the Android graphics team for that. I actually did reach out to Romain, really trying to find out if there's a way around that before the talk. But basically what he told me is that the way that paths are drawn is it's actually rendered to a bitmap, and then that is uploaded to the GPU as a texture. In their talk, I believe it was in their keynote, he also mentioned that one of the things that one of the optimizations they made, I think around Jelly Bean maybe, was rendering all of the system drawable components to one texture, so that can be shared with everything. So there are a lot of cases where that is the case. I'm not sure if that's necessarily the case across the board, but in a lot of cases, rendering a path and that sort of thing, it is. All right. And I think that's about it for my time. So if you have any other questions, I will be, I don't know, out in the hall or around the conference, but otherwise, thanks.